In this video, I would like to give a geometric definition of the parabola, the familiar parabola, but the definition, the geometric one, is often omitted, even in universities, and that's a pity, because this is really interesting, and the parabola has a very nice optical property. So the geometric definition of the parabola goes as follows. There's the special point f, which is called focus, f, 0. And if you think of focus in optics, then you're right, there's a good reason for this name. And so there is this point that is called the focus of the parabola, and we'll see its optical property. And there is this line which is called the directrix of the parabola. And the parabola is defined in the following way. It is the collection of all the points in the plane that have their distance from the focus is the same as this distance from the directrix. This has to be equal to that. And so this point over here, of course, is minus f, y. And so this distance, of course, now it's straightforward to derive the equation. So this distance is x minus f squared plus y squared, has to be equal to this. So it has the same y component. So we need to have x minus f. So it's actually x plus f squared. Or this means that y squared is x plus f all of it squared minus x minus f all of it squared. And that's an easy computation to see that this is 4f x. Okay, so that's what we get. It's really easy, because x squared from here is reduced with that x squared from here, and f squared from with f squared from here, and here we have twice xf and minus twice xf. That's what we get. Or in another way, if we write this, then x is 1 over 4fy squared. That's the equation, and that's a bit less familiar, or less, maybe you're less used to this. But if I plot this, then what we're going to have is this parabola here. Okay, and this is the same parabola, it's just the change of perspective, right? So if we just relabel the axis and we treat the x-axis as y and y as x, then this is the same. It's just the same as the parabola that we have, y equals x squared. So this is the same quadratic function, just a matter of perspective from where you're looking from. Because if we rotate this picture 90 degrees, then and call x by y and y we call it x, then we get the same picture that we're used to. And the parabola that we have in high school, right, the typical parabola, ax squared plus bx plus c. Let's suppose that a, of course, is non-zero, otherwise it's not interesting. So this can be rewritten as a, and here we have x plus b over 2a. It's a matter of simple computation, and here we need to take c and subtract b squared over 4a. That's pretty straightforward. And what it tells us, that the overall shape, if we have this function a is just proportional to x squared, right? So this factor over here, so how does this compare to the parabola? So say we have a parabola, just let's talk about the shape. Say we have a parabola ax squared, right? Then this parabola is of the same form, okay? And now if we add this factor over here, right, then if it's positive, then it's just a matter. So when we add this, it's a matter of shifting it, say, upwards. So it's the same picture, the same function, but shifted upwards. This results in adding this term. And now if we add this term into x, instead of x we do that, then it just is equivalent to moving it to a point, say here, minus b over 2a. This will be the vertex of the parabola, and this is the elevation, but it's all the same shape. So the most general quadratic function is still a parabola, the one that you're used to even from high school. That's the familiar parabola, but here we will adhere to this presentation. So actually this coefficient, right, this coefficient a that you are familiar with, and often in high schools and even universities omitted, that this a is actually 1 over 4f, and f is the focus of the parabola. But we will also, so here we will also demonstrate and with Desmos, and we'll visualize the optical property of the parabola. Okay, so now we can go to Desmos, and let's just start plotting this and see how it works. So here's our Desmos, okay, and let's start plotting. Desmos understands this. So if I write x equals 1 over 4f times y squared, okay, so Desmos will offer me to add a slider for f, and of course we want this. And of course, let's take f to be non-negative, and from 0 to 150, doesn't matter, and 0.1. And that's our parabola, and we see we have the slider for f here, of course, and we see how the focus affects the parabola. Okay, but now let's see those. Let's move it upwards. The control of the simulation or visualization. It's convenient to have it upwards. Okay, let's add some more things here. So let's call this point f, which is going to be f, 0. This is our focus, and let's give it a label. Let's call this focus. Okay, and let's also plot the directrix. Okay, we're done with that, and let's, I don't know, call it d. And so d is going to be just a point along the directrix, so it's going to be minus f, comma 0. That's our directrix. Let's just choose a color for that. That's going to be green here. Okay, and this is okay, and this, let's choose this to be purple. Yeah? Okay, done. And now let's plot the directrix. Okay, we have it here. So the equation of the directrix is x equals to minus f, basically. And let's just choose the color here, again, to be green. Okay, and we're done. Okay, so we have the directrix, and now we want to have this sliding point. So remember, if x equals to 1 over 4f y squared, then let's draw it parametrically. So we'll introduce the parameter f. So if, so if y is s, right, then x has to be equal 1 over 4f times s squared. Okay, and this is going to be our slider. So let's call this capital S. This is going to be this point. So let's add slider here, and let's give it a label. I don't know, we can call this point S as it, as a slider here. And okay, what color we can figure it out later. And let's give it a bit broader range from now, starting from minus 50 to 50, and let's give it intervals 0.1. Okay, so we now have this sliding point. Maybe I want to change its color so that it's better visible. Let's take it black. Okay, done. And so now that let's move this control slider for S upwards, and so we see this point as sliding. Okay, and now we want to see those lines for visualization that connect this sliding point S to the focus and to the directrix, and see this visually that those distances are the same. So now it's a good practice to give names to objects that you create, such as this S and such as this F and such as this D, because actually I want to take this point D. Let's call this minus f comma s, and so this is this point that we want. It's on the same height as this our slider, and that's the point on the directrix. And now if you want to let's label this I don't know, just D. Okay, so we can talk about points. So we have this D on the directrix, S sliding on the parabola, and the focus of the parabola. And okay, so now if you want to draw a line, so we'll do it in a vector way, and we have those objects defined. And I said previously that it is good to think of writing those commands in Desmos as in a way as software design, having in mind that it's modular and convenient. So s times s, you see, s times t. T is this parameter that we plot, so s is treated as a vector. So if we take s times t, it's plotted this line, but that's not what we want. We want to take 1 minus t and times this point, so we want to connect s to the focus. So this is f, and we see that it connected this line, and the reason for this is the following one. This is a linear combination of two vectors, and it is this linear parameter, so of course it's going to be a straight line. And the straight line, when t equals 0, it starts at f, and when t is 1, it ends at s. And since we're in this interval, the direction doesn't really matter, where is t and where is 1 minus t. So we've plotted that. For color, I don't know, let's make it purple, just for visibility. Okay, and then we can do the same for the directrix. Basically, we need to take this combination of now d and f, right? So it's going to be d times t, and here plus 1 minus t, but we connect it to the slider s. And so we have it. Does it visually seem to be equal? Supposed to be. Yeah, here it's visually seems okay. They have to be equal, just by definition, by the way that we defined it. So we see this sliding here, and this is nice. Okay, but I promised you the optical property of the parabola, and for that we'll need to make some more math. but just we've seen this initial like geometric definition come to life, and now we want to go farther and see the optical property. So we need some more computations. So let's go back to our parabola. Okay, and let's see. So this is our parabola, right? And so basically, this point we have parameterized it, and it's often convenient to work vectorial with this parametric representation. So it's 1 over 4f s squared comma s here, and this is like this curve, call it gamma s. And so when we differentiate gamma, we're going to have this velocity tangent vector. So this gamma prime vector, gamma prime of s, is going to be it's just 1 over 2f s, and this is 1. And basically this is the direction of the tangent vector to this point on the parabola. And of course this point is going to be, this is what we call the capital S, this is the sliding point, or we can call it gamma s if we want. And now this vector is the tangent vector. So in order to visualize this tangent line, what we need to take is it's a line that starts at s and takes a step of t, which is a parameter, in the direction of this the derivative of gamma prime. But maybe it's a good practice, let's normalize gamma so it's a unit vector. So let's call this vector t, which is going to be this unit tangent. So we'll take this, it's 1 over 2s, 1 over 2f, and this is times s, and 1, and just make it into unit vector. So we normalize it, this is 1, and here it's s over 2f, all of it squared. This is our unit tangent, and it's preferable. So let's just make it this way. So we take this s, and we take a step of size t in the normalized direction. So let's plot this tangent line. Maybe we'll plot something like this. Okay, so let's go to Desmos and add this and see how it works. And we'll add more things, because in order to demonstrate the optical property, what we need is basically we will create this collection of rays, and then with this collection of rays, when they hit the parabola, the angle of incidence has to be equal to the angle of reflection relative to the normal, and to get the normal, it is good to have the tangent first. So let's define the unit tangent. It's 1 over 2f times s. So it's at point s. This is comma 1, and then let's just normalize this. So this is going to be square root and of 1 plus, and here we're going to have 1 over 2, not 1. Let's call it s over 2f, all of it squared. So this is our unit tangent, and we do not. This is unit tangent vector. Of course, it's emanating from the origin, but we want to take this vector and to make this step from here. So we're not going to plot this. So now let's do what we are already familiar with. So we'll take the point s, and we will take a step of t in the direction of the tangent t. So what we see here, yeah, it's red here. So red on red, we cannot see it very well. So let's change the color here. So let's make it, I don't know, let's make it black. Done. And let's make it a bit longer for better visibility. No, 10 is an exaggeration. Let's take 5, and maybe from -5 to 5. Okay, that's a bit too much, but okay. What we see here, that when we play with the slider, we see that this tangent surface, the tangent line, or this tangent segment, is moving together with that, and we want to have the normal as well. So let's go then and compute the normal. So okay, so let's redraw it. Sorry for the redrawing. So here we have this tangent vector t of s. And it's a parameter. That's our parameter. And basically, to get the normal, it is enough to rotate. There's two choices of normal. They differ up to sine, but up to sine the normal is unique. So taking t and rotating it in 90 degrees counterclockwise will give us this normal, but for the purposes, because we want to deal with light rays here on the internal side that are being reflected, it's more convenient to work with this normal. So it's actually rotation clockwise in the negative direction. So if t is this vector, it's 1 over 2f up to the scale s, and this is 1 divided by the square root of s to f squared. This is the normalized. So basically the choice of the unit normal here is, so I'll write the correct choice, and so to choose it to be pointing inwards, we can perform the clockwise rotation here by 90 degrees. So it's going to be that, and divided by the square root of s over to f here, all of it squared. That's normal. And sanity check, when we take the product of this and that, we see that it is 0, and it's, you know, up to sign. The other normal is just changing the sign here. So let's, yeah, you know what, we have this normal, but maybe you want to talk a bit about reflection. So suppose that we have a line here, and the line, this line has this normal n, and we want to take a vector v, and we want to compute the reflected vector with respect to this normal. All right, this is v reflected when n is given. So how would we compute the reflected v? So we need to take this v, and we need to compute the projection. And it is convenient if n is this unit vector, because then the scalar product of v dot n hat, or I like writing the scalar product in this way. This is going to be, this scalar product is this exactly this length of this projection of v onto n, and if we subtract from v this part, we get to here, to this component, but we actually need to subtract this projection twice. And in order to make this color into a vector, we multiply it by the vector n again here. So this is this vector, and this reflected v is actually v minus twice the projection of, let's say, v scalar product with n on n here. This is v reflected. Okay, so and this is the reflection that we're going to be computing. So now maybe let's step into Desmos again and plot what our progress. So let us now define this normal. Okay, so the normal, as we said, we can basically take this, and we can take and copy paste it. Okay, and then we only need to make a slight adjustment here. So it's going to be 1 here, and then comma, and this is going to be minus. And so if we want to draw this normal over here, so we're not going to, yeah, again, that's, you see that's direction from the 0, but it's not something to be plotted. Actually, it's good to drag those that are not plotted, but just for the sake of definition and convenience, to drag them downwards. And okay, so now we would like to plot here this normal. So we would take this point s, which is the slider starting here, and we would like to go t steps in the direction of our normal. And okay, we can make it a bit longer, say 5, and the color, yeah, the color, everything is great about Desmos, but you know, the choice of colors is quite limited, but I hope they'll improve it. I don't know what color to choose. It's red, as all of them are taken. Let's make it black again. It doesn't really matter. Okay, done. Okay, so now we see this system here, that if we play with this slider, then it's moving, and yeah, it's nice. Okay, and now we would like to plot light rays. So let's call it, so let's create a list of parallel rays here. So I write like this, L for light, L stands for light. So let's see, they go here. Let's go from minus 30 and these steps of 1. So the next one is 29, and then 3 dots and 30. This is our list with 29 elements, and it will be quite useful to us. And then what we want to plot is we want to plot lines where y equals to L. And those are the lines here. But what we want is we want those lines to be limited to some range. And so the range here is that it's after the parabola. So it means this is the region where x is greater than 1 over 4f times y squared. And that's, we've limited the light rays, and let's choose, I was reserving the orange color because it resembles light the most of all the colors that are available so far. It resembles light the most, and so we can see the effect of the focus here, right? But Okay, we want to compute the reflection. So for each of those lines, for each of those, we want to compute. So basically what we can do is we can create this list of points on the parabola that correspond to the intersection point of each ray here. So if we were to take this S, as the, let's say it's just Control C here, and let's go over here, just Control V, and we'll replace S by L, we'll get the list of points. And L. Okay, so we have those points, they're red. Man, that's fine. I'm fine with them being red. We're not going to display them, it's just for convenience for the next step. And at each point, I would like to compute the reflected ray with the formula that we have derived, and then we will see that it is reflected all to the focus. Okay, so now let's go and make our final computation here. Okay, so now when we are on the parabola and we have this unit normal here and we have this vector, so this vector is pointing here, so we can take it as -1, 0, and we want to compute the reflected vector here, so we call this VR. So basically we need to take this vector -1, 0, that's going to be the direction here, so it's going to be -1, 0, and we need to subtract twice, and the scalar product of -1, 0 with n hat in the direction of n hat. Okay, so what are we going to have here? So it's going to be -1, 0 minus twice. So this is the x component of n hat. So I remind you that n hat is this 1 and here we have -1 over 2f times s. Okay, and divided by the square root of 1 plus s over 2f squared. And so the x component is going to be this 1 over this square root. So let me just, write this 1 over the square root, and you know what's supposed to be in here. And this is twice, so it's -1, and minus is going to be plus, so it's going to be plus twice over that, and times n itself. So we need to multiply it by the vector 1 and -1 over 2fs here, and this same square root, which we can reduce, okay, that we have here. So the reflected vector VR is going to be -1, 0, and here it's going to be plus, and okay, it's going to be 2, and here it's going to be minus s over f, okay, divided by this square root, no longer square root, it's just 1 plus s over 2f, all of it squared. So now let's go to Desmos and add this reflected vector. Okay, so let's go here, and not too original, let's call R for reflected, and the reflected vector is going to be minus, actually, maybe you can, no, let's just leave it this way. Let Desmos do all the required computations, and here we're going to have, so it's going to be 2. I need to take a peek to sneak. Yeah, like I say, it's 2, and then, yeah, because I forgot. 2, and here it's minus s over f. So it's going to be minus s over f. And here it's going to be divided by this expression. Let me just copy paste it. I'm being lazy. Okay, and this is reflected, but we don't want to draw this reflected ray. This is just the direction, right? We want to indicate the direction. And so what we want to take is actually for each light ray. So this is, let's take Control C and copy that to here. Okay, so we want to take plus, so this is t times all of that. Okay, so we'll see what we want here. So it is this vector, but I want to replace s with L, of course, because it is y. So let me replace every s with L here. Okay, and let's make it a bit longer and see if it goes into 10. Yeah, let's make it 10. Yeah, and basically we see that it all goes to the focus. So maybe, yeah, it depends. So the parameter, I mean the lengths, I could have drawn the lines in a parametric equation with their full lengths, and then they will be interfering. So let's make some, like this, call it 2f here. So it's focus dependent, and let's change the color here. I don't know what color. Let's go here and see this color, make it green. I don't know. Yeah, green is nice. Okay, and make it done. And so let's see how the effect of the focus here. So let's go and see, and maybe zoom out a little bit. Yeah, and if you want to limit, let's see again. So let's go here, maybe increase the focus a little bit. Right, nice. Oh, this is beautiful. Yeah, absolutely beautiful. And let's make it not, maybe up to F would be enough. What do you say? Yeah, just enough. Let's take 1.5 F for aesthetic beauty here. So we see that all those incident light rays are reflected to the focus. We've made the computation. We computed the normal here. We could also plot unit normals, but maybe will be cumbersome. So, and if we want, we can also the plot of this parabola. We can say that from here we can limit it to minus 30, smaller than y, and up to 30, and then we have this. It's like this satellite dish, and it's not coincidence that satellite dishes, if we go here, for example, or antennas, right? They have this. The hyperbola also has this property, this optic property. It also has focus. But suppose that this is a parabola, and we actually need to take this parabola and make a surface of revolution around this axis, right? And then we have something that focuses from this direction. So those light rays that are coming here, they will be focused at the focus, and that's where they put the receiver. So if you remember the constructions of those satellite dishes, then the receiver is somewhere here, and then it is designed so that all these electromagnetic waves, radio waves, or other electromagnetic signals are hitting this metallic surface, and electromagnetic waves are reflected from this metallic surface, and they would be reflected in the geometrical optic approximation exactly to this focus, so that the receiving quality is maximal. So that's the idea with the design of parabolic and hyperbolic antennas. And want to show Desmos again. And so that's what we see here. Okay, and so hope that it was interesting and useful to you. And this Desmos is going to be available in the description. So feel free to play around with this, to change parameters. And I really want to thank you for watching. Hope that you enjoyed, and hope to see you in the next video.